Hi everyone, it's great to see you here again. Now, you're looking at the same familiar streaming telemetry dashboard that the lab that we've shown so many times that you're probably wondering, okay, Roman, get help. Why are you showing this to us again? Has anything changed? Did you add something new? And actually, the reason I wanted to record this video is that we have quite some important news to spill. And the reason I wanted to show this lab to you today is that this whole lab, the 5 leaf and spine SR Linux switches, the full streaming telemetry gNMI stack, streaming telemetry stack with gNMI, Prometheus, Grafana, the stack with login software powered by Locky, and the 3 clients that are pushing traffic with iPerf, sitting next to my Chrome browser with 45 tabs, and the recording software is checking this video recording. All of that is running natively on my Mac, and it doesn't break a sweat. So as you've guessed, we will talk about today how to run Containerlabs on ARM, why it is now more possible than before, what challenges we had that stopped us from enjoying Containerlabs on ARM, and what challenges we still have so that you know all the caveats ahead of you when you want to run Containerlabs on ARM. But again, there are some major breakthroughs in the way you can run labs on your MacBooks or on any system that runs on ARM architecture, and we will dive deep into this today. Now, I will introduce chapters to this video so you can skip on the theoretical part and go to the practical part where I will show how to run this particular demo on your Macs. But I would suggest that you are not skipping on the theory as well, because it's quite interesting and not a lot of people know how actually Docker runs on Mac and what are the limitations and challenges we had to go through. So let's go and dive deep into this topic. All right, so we will start with the biggest question. Why do we care about ARM architecture? There is a good chunk of users who use MacBooks, and Apple switched from x86 chipsets to their own M chipsets that are powered by ARM architecture. So there's a very big number of users who would want to run networking labs on their MacBooks, me amongst them. And not only Apple moved to this ARM architecture and got us this huge benefits in battery life and performance and whatnot, but also recently Microsoft released the Surface laptop, and Surface actually runs on ARM as well. So you will have your Windows on ARM, and all the application needs to be running on ARM, etc., etc. So both Apple and Macs have moved to, or are moving in Microsoft case, to an ARM architecture. So having, as you can imagine, having the ability to run labs on your laptop directly without having internet connectivity or having a VM that you connect to running in x86 to run your labs is a very big and important thing to have. Like, I would like to run my labs locally. I only run them remotely because of the challenges that we've had with labs. But not only personal computers could benefit from this. You also know that there's a good number of ARM servers in cloud providers. I don't know, like AWS, GCP, Hetzner. You can go there and book a VM that would be running on ARM architecture. And typically those VMs are cheaper. So you can get more power out of ARM server for less bucks that you would pay. So as you can see, there's a very good reason why we should care about running Containerlabs on ARM. But then why did we, oh yeah, by the way, we can also run Containerlabs on Raspberry. Raspberry has been rocking ARM architecture for years, like since the beginning. So you can technically run labs on Raspberry. And there are some LinkedIn posts explaining how they run some labs on Raspberry. So you can explore this way as well. Probably you want to install Kubernetes on Raspberry and run a cluster of Raspberry Pis and install a lab on them. You bet. Okay, so why we only started to talk about ARM-based labs now? Well, that is because we had quite substantial challenges ahead of us. And the first and foremost challenge was that you need to have a network operating system that is natively compiled for ARM, meaning that your Nokia's, your Juniper's, your Cisco's, Aristas have to be compiled to ARM architecture in order for them to be natively running on the target ARM-based architecture. Whenever you have an uncompatible pair, meaning ARM host and x86 network OS, you will have to run through translations from one set of instructions to another. So you'll have to run a VM, and it's always comes with a performance penalty. And this performance penalty is quite crucial for network operating systems. Some of them will just not boot if there is like a translation layer in between. That is why the most important piece was for us as networking community to come up with ARM native network operating systems. And we'll talk about the list of these systems in the couple of next slides so you get a better understanding what exactly are we talking about. Second of all, you need to run Docker on non-Linux systems. And that is the case for MacBooks or macOS in general. macOS has a Darwin kernel. It's not a Linux kernel. And Docker will not run on Darwin natively. What Docker does is that it creates a VM which runs Linux on top of macOS in case of Apple, or it can be VSL in case of Windows, but essentially it's kind of like a VM that powers Docker on non-Linux systems. So you can think about that whenever you want to run Docker on something that doesn't run Linux natively, some kind of a VM would be required. And the third challenge, which is more related to Containerlab probably and to Docker in a lesser extent, is that you need to have Linux networking primitives or APIs, if you will. Like when Containerlab creates VETH pairs, namespaces, IP tables, it needs to talk to a common set of APIs, being Netlink or something like that. Without having those APIs, it is impossible to run Containerlabs. So again, you will have to run a Linux VM. We need to have Linux in order to create labs. So these were like the three main pillars or the three main challenges ahead of us that prevented us to have the same amount of labs that we've created so far for x86 architecture. It prevented us to have the same set of labs for ARM. So now, when we know what challenges were ahead of us, let's talk about the biggest one, network operating system support. And that was the catalyst for this video, obviously. Since I affiliated with Nokia, I'm glad to say that we are, again, first here out of the, I would say, big vendors blog who offer you a native ARM container image that you can, again, download publicly free with a single Docker pull command, no tokens, no registrations, same free for all container image. But now this container image is compiled for ARM architecture specifically. Now we offer this as a preview right now, meaning that there might be some issues, although I haven't seen them when I was playing with it, but I want to make this caveat right now, so it's not an image that will be released as frequently as the x86 image, but we are moving to a point where we will be able to create a single manifest which will encompass x86 and ARM architecture. The good thing is that you can already start with Nokia Solar Linux on ARM right now, as if it was a properly released image. It's just like a small caveat that we put here to make sure that we can get you all a preview image so you can start playing with it. Now, second thing is that it's not only us who are looking into this, right? Arista promised to release COS image for ARM in 2024, maybe later, but they promised to, or maybe I shouldn't say they promised. They're working on this, considering the open messages that I got through LinkedIn. So we will have two major vendors with ARM systems. One is already there. Nokia Solar Linux is already there. One is probably coming. So we will have a good amount of labs that could already be running on ARM. Unfortunately, I haven't heard any news from Cisco camp, so I don't know if XRD can be compiled for ARM64. Maybe it can, but again, I haven't heard any news from them, at least in the public space. With Juniper, the CRPD component, which is just a routing component, so you have to understand that it's not a fully operating network operating system. There is no data path, emulated data path that you can run. It's just like the management stack. The CRPD has been provided with ARM support for quite a while. Now, the only challenge is that, of course, it's just a management software, so you can't do much on the data path with it. But again, for things like management stack, it's already in ARM. So as you can see, 2.5 out of 4 big vendors have something to offer you right now or promise to offer you very soon so that you can run labs on ARM. What about other network operating systems? Well, FRR is a very good example. FRR has been compiled for ARM for, I don't know, for years maybe, but for quite a while. Now you can download FRR container in ARM architecture already now, and you could have done this probably a year before, which is great. That means that you can create a lab that is very close in syntax to some other systems that you are familiar with, and that system would run on ARM, meaning on your MacBook, on your Microsoft new Surface laptop, or on an ARM server. As for ViOS, I haven't heard any news. I would like you to correct this post if you know if there is a ViOS for ARM. That would be dope. I just couldn't find it. Same goes for Sonic. I'm pretty sure that they do not publish an ARM version for their community Sonic container, and it probably will be quite a challenge to build it for ARM if you would like to do this yourself. But again, if you know how to do this, that would be very beneficial for the community. And same for CVX. With CVX and Cumulus, it's even probably more challenging. There is no official vendor backing for this image. It was a network op colleague who built it, but then since he moved out from NVIDIA, I guess the image is a bit in limbo. So that's the state with containerized network operating systems. You probably figured it out that this is all about the containers now. But what about VM-based images? And on this slide, I ran out of good news, to be honest, folks. So the problem is that all VMs that I know of are only compatible with x86 architecture. That means that the SROSs, IOSXR, VGNS switches, all of that good chunk of VM-based images, they will not run on ARM. And especially on macOS, where there is no even support for nested virtualization, so you will not be able to run CAM or KVM and try to boot those images with translation from x86 to ARM. But even if you could, I would say that the performance penalty would be so crucial that most of the images will just not boot. You still can probably try this on ARM servers if that's your target architecture, but I doubt that you will have some good time. So it feels like we will have a better way forward with pure containerized network operating systems when we talk about ARM architecture. I do not expect vendors to rebuild their VM-based systems to ARM64. Maybe they will do, and that would be great. But I don't feel that this is the sentiment that they would like to pursue. So that's a bit of a bad news. But anyways, running containerized network operating systems is, I think, how I would like to see the future of networking labs or digital twins or network emulation in general. Okay, so what about non-network images? And that is one of the benefits of Containerlab or Containerlabs in general. We always were saying that, it's not only networking images that comprise the networking lab. More often than not, the great labs have some additional components attached to a network because, again, the network is something that provides a service to a business. So it's not a unit in and itself. It's more like a medium for applications to talk one to another. And these applications, they can be added to Containerlabs so that you can have a better picture, like the more complex and complete lab. So we're talking about these telemetry stacks, the traffic generators, the route servers, RPKI validators, network automation stacks, databases. You feel it. It's something that brings the application part to the networking. And the good thing is that most of these applications have been already compiled for ARM. So it's easy to build a cross-compiled Go application. That is why every Go application can be easily compiled for ARM and x86 without investing too much. And quite a lot of these applications are created in Go or Rust, and cross-compilation is quite good on with these languages. So as you can see, everything I show here can be already consumed on ARM architecture natively. If it's not that hard to build it. And that's the beauty of it. If it's an open source project and it's only being released as an x86 container, you can build an ARM version of it yourself. So you don't have to really wait for an owner of the application to do that if you want to onboard this to your ARM Containerlab. Okay, so let's talk about the images and the manifests. How can you make sure that you have an image that is already ARM compatible? So there are two kind of subtle differences with how ARM-based or multi-architecture images are distributed. You can see that one of the approaches is that when you have two manifests, one for an ARM version of a container and another one for another architecture like AMD 64 and ARM 64, and there are two separate manifests. That means that you will use two different Docker pull commands to pull those images. Like in the example with SR Linux, once we released the preview image for ARM, we decided that we do not want this to be a single manifest because currently it's a preview, so we will want to specifically call it out. So when you type Docker pull, you know that you're pulling a preview image. That is why we created a separate manifest for this image. So when you type Docker pull SR Linux 24/7.1, you will pull the x86, the official x86 container image. But if you need to pull the ARM version, we created a tag -arm-preview that would be associated with this image. So when you would want to pull the ARM image of SR Linux, you will have to look up the tag, and specifically call it out. So this is the way, one of the ways to provide multi-architecture images on any container registry. But there is another way. There is also a multi-arc images with a single manifest, and it's actually a better way to package things with multi-arc support. That means that a single manifest contains references to different architectures. For example, consider one of the most popular Linux container images, Alpine. With Alpine, a single manifest has kind of entries or sub-entries that says whenever the target architecture is x86, you will pull this image. When the target architecture is ARM64, you will pull the other image. But the manifest stays the same. That means that if you use Docker pull Alpine on an AMD 64 architecture, you will pull the native architecture for a system. But the same command typed on the ARM64 architecture will download the ARM version of it. So these are the two ways that you need to be aware of. Quite some subtle differences between the two, but still interesting to know that there are two things that you can find in the wild when you will try to look up for an ARM image. So now let's switch gears and talk about Containerlabs on macOS. How it runs, how Docker runs on macOS and on ARM in general. And we will dive into some interesting details how to actually do that and how I do this, given that I've tried quite a lot of ways to run labs on macOS, and I will share what I find being the most native performant and suitable way as I feel it to run Containerlabs on macOS. Okay, so let's start with Docker on macOS. How does Docker run on macOS? Well, there are two major components involved in Docker on macOS. There is a Docker CLI, which is a standalone binary that runs on Darwin on the architecture of your macOS. Like on this slide, you see that I'm showing the M chip based macOS. So the Docker CLI component would be running on as a Darwin binary for ARM64. But the actual Docker daemon and the containers that will be running will not be running on macOS. They will not be running on Darwin. They will be running in a VM that is provided by one of the software that delivers Docker support on macOS. And it can be Docker Desktop, it can be Rancher, it can be OrbStack, it can be Colima. There are many projects that add Docker support for your macOS. But what I wanted to show here is that it's always a VM that is involved when you run Docker on macOS. And the CLI that runs natively in your macOS just talks through the sockets to the daemon that runs in a VM. So that is a subtle difference. When you switch to an Intel Mac, nothing changes. It's just that the VM that would be running on macOS will have to be running in the AMD 64 architecture, but it will still be the Linux VM that runs in macOS that delivers the Docker support. And again, the CLI component will be running natively outside of this VM so that you can type in your macOS terminal docker run hello world, and you will immediately see an output from the container as if this container would be running natively in macOS. So all of these software, Docker Desktop, Rancher, OrbStack, they try to hide the VM presence and make sure that from the UX perspective, it's as if you run natively Docker on your macOS. So why don't then we can have Containerlab running in the same way, natively on macOS, talking with API to Docker, and live happily ever after? Unfortunately, that is not quite possible. And the reason is that whilst Docker Containerlab talks to Docker API, that's how we spin up containers and do this Containerlab thingy, we also heavily rely on Linux APIs. We create path links, we create namespaces, we deal with IP tables. We do rely on Netlink quite a lot. And those APIs, they are not available in macOS Darwin, right? That is why Containerlab cannot really be installed natively in macOS. But then how do you want to run Containerlab? What are the ways? And the way is actually to put the Containerlab component inside the Docker VM. As you remember, this is a Linux VM. This is where VHH can be created. This is where Netlink exists. That is why we want you to install Containerlab in a VM, and that would make it very much alike to how you run Containerlab on Linux. Because again, this would be a Linux VM. It just happens to run on macOS, but from the user perspective, you would not notice a difference. And through the demo, I will show you how to get from a bare macOS installation to a running lab, and you will see how fluent and how unobstructive the whole process is. So yeah, keep in mind that we want to have Containerlab as a component, as a CLI running inside the Docker VM and not outside in macOS Darwin. So okay, how do we create those Linux VM in macOS? So there are two VMs that you can actually deal with. One is what I call the integrated VM. The integrated VM is a VM that is by default created whenever you install Docker Desktop, Rancher, OrbStack. That is the VM that makes containers run when you type Docker run on your macOS terminal. But this VM is kind of shared. It's the VM that runs the containers, and it's meant to be invisible to a user, but it's also not meant to be SSH'd into. They try to hide this VM from you. They want to make sure that your UX is fluent. You don't want to think about the VM itself. That is why this VM is not a great fit for us to install Containerlab into, because it's just not meant to be consumed as a proper VM. But quite a lot of projects that add support for Docker to your macOS, they can also create standalone VMs. They can act as a hypervisor or an orchestrator for your VMs. And with these software solutions, you can create a standalone VM And in this standalone Linux VM, you can install Docker CE and Containerlab exactly the same way as you would do on Linux. It's just that we want to have a Linux VM natively integrated with macOS, easily installable, running smoothly, and integrated with your workflows so that you don't think about the VM as much. And there is a software that does that. And I wanted to talk about this because I tried all of them: Docker Desktop, Colima, Rancher, a few of CLI tools purely from the open source. And I found that the Orb stack is probably the most satisfiable software that adds Docker support on your macOS, but it also has a way to create VMs on your macOS. But it's not just a VM manager. It's not UTM, as if you are familiar with this software. It's more integrated with your macOS. And you will see what I mean by saying integrated, which features OrbStack has that are absolutely killer and made me reconsider doing the local development on macOS instead of connecting to my dev machine in a cloud. It has a free version for personal use, so you can use every feature of OrbStack. And we will be using OrbStack here. So I wanted to show you how I use it to create Containerlabs on MacBook that I have. So the demo procedure is rather straightforward. 4 steps. We need to install OrbStack. We have to create a VM. We install Containerlab there, and we run a lab. 4 small steps, but I will dive into details so that you have a better understanding of what it is and how it works. So let's start with the OrbStack. Well, I will skip the installation part because it's super trivial. I will just show you what you get when you install OrbStack. It's a native Swift application for Mac. It comes with a UI, but it also comes with a CLI. So I could have used CLI to create a VM, but I wanted to show you this in the UI so that maybe that is how you would use it most of the time. So you have your UI that says, here is the containers that you can run, and here's the Linux machines that OrbStack can create for you. Now let's create a new Linux machine. So I will name my machine CLab. I love Debian the most. I run Debian 12 Bookworm. And as you can see here, there's like 2 types of CPU that you can select from. It can be an Apple CPU, and that is what I'm running. I have the M1 machine here. And you can see that if you're running an Intel Mac, you can just switch to Intel and you will have exactly the same experience, but you will be just running an Intel VM. And then, of course, you can benefit from all the x86 images. So that's great. But we are running on ARM-based Apple Mac, so we will have to make sure that we are selecting the proper CPU type Apple. So now we are creating the VM. Notice how fast the VM takes to be created. So it's been like 5 seconds and the VM has been created. When we created a VM, how do we actually consume it? Well, of course, the easiest way would be to SSH to the VM. And this is what I mean by integration that OrbStack provides to you. When you create a machine in OrbStack, OrbStack has a lot of integration that happens behind the scenes with your macOS. See that I can just type SSH orb and I'm immediately in my VM. Now, what it means is that they took away all of the pain for you to figure out how to connect to your VM. It all happens automatically in the background. They install the SSH config files, they make it keyless. It's absolutely amazing, the attention to details that this project has. With SSH orb, I'm connecting to the machine that I have created. Now, as you can see, this machine is a specific OrbStack kernel that runs, but it's a Debian 12 machine. So if I do OS release, cat OS release, you will see that it's Debian Bookworm. Amazing. So now we have a VM already running and created. What OrbStack claims is that when you do not use the VM, the performance penalty of running this VM is negligible. They claim that you will not notice this VM is actually running. And I can say that I've been running this lab for quite a while, as you can imagine, and I haven't noticed any substantial performance penalty whatsoever. Once we will deploy the lab, I will show you the activity monitor and what it consumes, but the performance penalty is really low. So that is absolutely amazing. So now that we have the VM, the step number 2 is install Containerlab. Now, installing Containerlab is absolutely easy. So now with the quick setup script that we have, you can just copy paste the command from the installation documentation piece, paste it here. And what we will be doing now is that we will be installing Docker, we will install Containerlab, we will install GitHub CLI tool, and yes, it's gonna be like 30 seconds, and after that, everything is ready to go. Now, every software package that we are pulling now will be ARM64 native. So if there is something that is not available in ARM64, Rosetta, the virtualization piece in macOS, will kick in and it will translate x86 instructions to ARM64. But most of the software has already been compiled to ARM64, so we will run everything absolutely natively. So now, as you can see, Containerlab, Docker, everything has been installed. And now we can proceed with running a lab. Here's another piece of integration that happens with OrbStack. Like, I love to develop in VS Code, and I like to open my labs in VS Code, and I want to use the same way of dealing with labs in my Mac as I would do on Linux machine. And what I can do with OrbStack is I can use the Remote Explorer in my VS Code. And with Remote Explorer, there is this orb machine detected automatically because orb creates the SSH entry for the orb machines. So I can connect to this local virtual machine using the Remote Explorer, meaning that I will establish the SSH session to the orb machine, and I will install VS Code server component. So I can do all of that. But check this thing. If I open the file browser on this orb machine, I can get access to my macOS file system. Again, this is something that happens automatically. You don't have to think about it. Like if I go to /users, here's my macOS user, and I get access to my whole macOS disk. So I can go to the projects directory that I have on my Mac. It's not in the VM, but because it's mounted to the VM by OrbStack automatically, it's automatically available. So I don't even have to think about mounting separate folders to my VM. It will be taken care of for you. Now in this folder, I have this SRL telemetry lab cloned on my Mac, not in my VM, but it's propagated through the mounting of the folders to my VM so I can get access to it. So if I open this open this folder here, I get access to a folder on my macOS from the VM that I have, okay? Oh, by the way, I wanted to show you one little trick that we also added to installation script of Containerlab. So now we can set up a very simple bash prompt, but it's way better than this long one-liner. So if I call this script, which is just downloading the quick setup script and executing the setup bash prompt function. So if I do this and reopen the terminal, I will have a 2-line prompt, which is way cooler, way more usable as far as I am concerned, but I think you would love it as well. So now with the nice prompt installed, you can see that I have my streaming telemetry lab topology definition file opened. It still mentions the original x86 SR-Linux version. And what we need to do is that we need to change this to this ARM preview image that I've mentioned. So how do you know which tag to use? Well, if you go to SR-Linux container image GitHub repository, you will see all the tags that we've pushed to date to GitHub Container Registry. And you can see here that 24/7 ARM preview is the tag that I need to use. So what I will do now, I will just copy this pull command and I will do docker pull, and I will paste this tag 24/7 ARM preview. Okay, if I can type, yes, you can see that I cannot, so I will delete this. Okay, so now I'm pulling the SR-Linux container image that has been compiled for ARM with data path component, with management stack, exactly the same code that you would be running in hardware. So now I'm pulling this from the internet. As you can see, I have not logged in. It was a pure VM with no Docker, with no credentials installed, which proved the point that the image is free to pull for everyone. And once the image is there, what I can do is that I can just change the reference here to 2472 ARM preview, save the topology file, and now we are ready to go. We can type sudo clab deploy and hit enter. So now Containerlab will pull the rest of the images that were not there. And remember, we just installed Containerlab. We haven't pulled any images besides SR Linux. So every other image, the Alpine image, the network multi-tool image that we use for clients, the gNMIc, the Prometheus, the Grafana's, they will be pulled from Docker Hubs or relevant container registry by Containerlab. And because we are running on ARM, Containerlab or Docker API will figure it out, will use the proper images to pull. So the images that we are pulling now will all be ARM64 compatible or ARM64 native. They will be compiled for ARM. But then how do you know? I think it's quite interesting to see how can you tell that the image is ARM native or not? Well, you can do docker inspect, and you can use one of the images. Like let's take gNMIc, like docker inspect gNMIc, and if we go all the way up, you will see that there is an architecture string here, and it says architecture AMD 64. So that means that this image is not ARM native. Now, why is that? So that is because the gNMIc does not compile, does not create container images for ARM64 architecture, and we will definitely fix that. But the good thing is that you can see that even though the architecture is AMD 64, the gNMIc component runs. The way it runs is that the Rosetta component in macOS can translate and support the x86 or AMD 64 instructions, transpile them or convert them to ARM64 instructions and run in an ARM64 VM. But then let's try something else. Let's actually look at SR Linux. So if we do docker inspect and we'll use the SR Linux image and we check the architecture here, you see the architecture here says ARM64. So this image is native for ARM64 architecture. And of course, you can check others. You can check, Promptail, you can check Prometheus, etc., and you will see if they are native or not. All right, so now once we installed Containerlab and we spin up our lab, we see that some of the components run natively as ARM64 images. Some of them are AMD64 powered by Rosetta so that they can run. How do we get access to, let's say, Grafana? And that is, again, one of the integration beauties that OrbStack provides. When you launch a VM in OrbStack, it creates the multicast DNS or MDNS entries because they run the orbstack.local domain zone. That means that I can type the machine name that I have. Remember, I created a machine name with name clab. And if I type clab.orb.local and the port that I have exposed in my topology, for Grafana it's 3000. If I just use this, I get access to a Grafana. So I don't have to think about the port propagation, the exposure, the IP tables, the netting. It's all taken care of. And of course, if I just open up this topology, the dashboard, you will see that it runs. Everything is working. The gNMI is collecting the data from the nodes and it's rendered. through the TSDB queries, etc., etc. So everything runs. And that was the whole point of the demo, to show you how you can do this easily now with macOS, given that you use the images that are compiled for ARM architecture. And with a nice software such as OrbStack, you can really think about labs more than the infrastructure struggles to get through to run them. So I hope you liked it. I will add some comments in the descriptions to a text version of this demo and the explanations. They will probably appear a bit later, but you will have the textual version of all this. We will have a proper ARM64 container image for SL Linux later down the road. It will be in a single manifest, so you would be able to just do docker pull ghtr/nokia/SL Linux. And if you run it on ARM, the ARM image will be pulled, so you don't have to think about tags anymore. Check this out. I hope you will enjoy it, and let me know if you want to know more about how to run labs on ARM architecture and macOS. Cheers.